Umar thinks that a plus 1 all squared is equal to a squared plus 1 for all values of a. Show that he is wrong. Well, different ways you could do this. The most obvious way is to expand these brackets out and show what it actually equals. So if I was to do a plus 1 all squared, that means a plus 1 times a plus 1, which is a times a, which is a squared, a times 1, which is a, plus 1 times a, which is a, plus 1 times 1, which is 1, which is a squared plus 2a plus 1, which is not the same thing as a squared plus 1 for all values of a. So that's the most obvious way I think most people would answer that question. Alternatively, you could pick a value of a, any value of a, and show that this is not correct. So when a is, 10, 10 plus 1 squared, 10 plus 1 is 11, 11 squared is 121, 10 squared is 100, plus 1 is 101, and obviously 121 does not equal 101. So you could do it with what's called a counter example to show that it's not true for all values, but I think most people would do it this way. Anyway, moving on, here are two right angle triangles. We've got the measurements in centimetres, and we can see we've got this right angle triangle where A, B and C, and this right angle triangle A plus 1, B plus 1, C plus 1. And we need to show that this is true. Well, from the first right angle triangle, because it is a right angle triangle, I can write down Pythagoras. And I can do a similar thing for the second right angle triangle. A plus 1 squared plus B plus 1 squared equals C plus 1 squared. I'm going to expand this out. So a plus 1 squared I know is a squared plus 2a plus 1. I'm not going to show my working out for that bit because I've already done it up here. Similarly, this will be b squared plus 2b plus 1, and this will be c squared plus 2c plus 1. Now I'm just going to rewrite this ever so slightly, and you'll see why in a moment. I'm going to rewrite this as a squared plus b squared. So I'm just collecting those squared terms together. And then I've got the 2a plus 2b plus 2 when I add those ones together. And over on the right hand side here I've got the c squared plus 2c plus 1 still. The reason I've decided to group those things, the a squared and the b squareds together, is because I know that a squared plus b squared is c squared from the first triangle. So I can replace that a squared plus b squared with c squared. And now I've got a c squared on both sides, so I can cancel those out. While I'm at it, I'm also going to subtract 1 from both sides. So I get 2a plus 2b plus 1, which is equal to 2c, which was what I wanted to show. And then finally, it says a, b and c cannot all be integers. Explain why. So we're following on from part B of the question. Why is it that this shows that they can't be all of them integers? Well, again, different ways of explaining this. The way I would do it, I would put all of the a, b and c on one side of this equation. So I'd say 2a plus 2b minus 2c equals minus 1. So I'm just swapping this 2c and the 1 around. So I've got the a, b and c's all on the same side together. And then I'm going to divide everything through by 2. So a plus b minus c equals minus a half. And the reason why I've done that is because a, b and c, if they were integers, so if a, b and c were all integers, then adding or subtracting them, adding and subtracting would also give an integer. If you add integers together or take them away, then you're going to get an integer. So if a, b and c are integers, then adding them and then taking them away, that would give an integer. But it doesn't. so they can't be integers. So A, B and C cannot all be integers. There we go.